So far, we've talked about basic probability, independence, joint probability, and conditional probability. We're now ready to start talking about Bayes' theorem. Bayes' theorem is where the naive Bayes classifier gets its name. You see, a long time ago, in the 1700s, in Kent, England, there lived a clergyman by the name of Reverend Thomas Bayes. Thomas Bayes got very interested in probability later on in his life, and he came up with a neat little trick. Let's go back to our weather example. With the conditional probability formula, the hardest part was this joint probability term. Namely, what is the probability of it raining and being cloudy? Now it turns out one can phrase the conditional probability formula in another way. Instead of having this joint probability in there, we can have another conditional probability. Namely, given that it is raining, what is the probability of it being cloudy? Now, this is different from given that it is cloudy, what is the probability of rain? These two are not the same. Have you seen rain on a sunny day? Yes, but not very often, right? The probability of clouds when it is raining is probably around 95%. On the other hand, the probability of it raining given that it is cloudy is probably more around 40%. So these two numbers are as different as the conditions. But the point I'm trying to make here is that changing the top part of this fraction in this formula is all Bayes' theorem is. Reverend Bayes basically figured out how to reverse a conditional probability in the formula to make this whole thing easier to calculate. The conditional probability looks like this. Here's the generic formula for Bayes' theorem in terms of A and B. And you'll find this theorem very early on in any statistics textbook. But let's go back to our spam example. Given that the email has the word Viagra in it, what is the probability of this email being spam? Using Bayes' theorem, we can now calculate the same probability like this. Using this formula, the calculation becomes very easy, and that's why I'm harping on about this so much. Let's tackle one term at a time, starting with the probability of spam. We've actually already discussed this. We figured out how common spam emails were. This was 55% in 2017, if you remember. So let's plug that number in here, 0.55. Now, what about the probability of the word Viagra coming up in an email? To calculate this number, we have to figure out how common the word Viagra is in emails as a whole. How often do people use the word Viagra in an email, both spam and in normal emails? Say we've looked at an enormous data set of emails containing 700,000 words across thousands of emails, and we count how many times Viagra gets mentioned. If the word Viagra gets mentioned 75 times, then the probability of Viagra coming up in an email is 75 divided by 700,000. In this case, we're just applying basic probability, just like with our calculation of the probability of getting hit by lightning. We take the total number of times Viagra gets mentioned, and we divide it by the total number of words that we looked at in our data set. Next, let's tackle the probability of Viagra being in an email given that the email is spam. What does this mean? This is a conditional probability. Given that the email is spam, what is the probability that the email contains the word Viagra? How would we calculate this? Again, we look at the frequency of the word Viagra, but this time just within the spam emails. This allows us to figure out what is the probability that an email contains the word Viagra given that it is spam. And looking at our data set of emails, we count the number of times the word Viagra occurs, and we look at the total number of words in our data set that are in spam emails, say 370,000. If we find that the word Viagra appears 65 times, the conditional probability is simply 65 divided by 370,000. And that's it. We've got all our numbers. We can work out the probability that an email is spam given that it contains the word Viagra. And based on our data here, the probability is around 90%. What this example shows is that the frequencies of a word really are key. By looking at the frequencies of a word in spam messages versus all messages, our algorithm learns which words are spammy. The reason we think words like online pharmacy, double your cash, etc. are spammy is because these words often appear in spam emails. But the story doesn't stop there. If we look at an email message, then we're going to have more than one word in the email body, right? Well, that depends on your friends, actually. But my point is that we can calculate the conditional probability for every single word in the emails in the entire dataset. Not only will we have worked out the conditional probability of an email being spam if it contains the word Viagra, but we will have worked out the probabilities of all the other words as well, like expert, free, cash, and so on. So now when an email comes in, what if it has both the words free and the word Viagra in it? What's the probability of an email being spam in that case? Let me rephrase that. Given that the email has the word free and the word Viagra in it, what is the probability that the email is spam? At this point, we've come full circle, all the way back to joint probability. Remember how, with the coin flipping example, we simply multiplied the probability of heads times the probability of heads to figure out the chances of getting two heads in a row? The reason we could do that was because the two events were independent. And this brings us to the naive part of the naive Bayes classifier. The reason our algorithm is naive is because it assumes independence between the words in the email. In other words, if our email has both the words Viagra and the word free in it, we can multiply the two probabilities together. And we can do this for every single word in the email. The more and more spammy the words are, the higher the final number. Now, let's continue with this line of thinking. If an email has lots and lots of spammy words in it, it's probably spam. And if an email has very, very few spammy words in it, it's probably a normal email. So this brings us back to the final decision where we compare two probabilities. Say we have an email with the words, "Hello friend, want free Viagra?" Well, using Bayes' rule, we can calculate the conditional probabilities for all these words and figure out what the probability is that that email is spam. Then, using that independence assumption, we multiply all these probabilities together to get a final number, namely the probability that the email is spam. And then we can compare this number to the probability that this email is a normal email. So for that first term, we would have, given that this email contains the word hello, what is the probability that the email is a normal email? Next, given that this word contains the word want, what is the probability that we have a normal email? And so on. We then multiply all these probabilities together, and then we can do our comparison. This is the classification step that we talked about in the very, very beginning. We will classify this email simply based on which final number is higher. What I've just described to you is called the bag of words approach for classifying documents. Each word is looked in isolation, and the frequency of each word becomes a feature in our machine learning model. And the fact that we've looked at each word in isolation is why this model is called naive. We're treating each word separately. We're ignoring grammar. We're ignoring sarcasm. we treat the city name New York as two separate words, new and York. We're treating the phrase not bad as two words, not and bad. The context is lost with the bag of words approach. The dependencies between the words are ignored. We are assuming that the words are independent. Like, well, words in a bag. At this point, you're probably skeptical. Will this really work? This whole approach seems super strange, and the assumptions also seem really crude. Well, I don't want to spoil it for you. You'll find out just how well this works in the coming lessons. And now that we've covered the theory behind the naive Bayes model, our path for the Python code is clear. The first step will involve extracting all the text from the email bodies. And this means moving on to the next parts of our project workflow, namely cleaning and exploring the data. For example, we will need to figure out just how common each word is in an email. We will need to do this for every single word, not just spammy words like Viagra, but every word. How often do people use the word Japan in emails? How often do people use the word weekend, Apple, Android, computer, lawyer, or friend in emails? We will need to count how often these words appear in all the emails in our dataset. And we have over 5,000 different emails in this dataset that we're working with. And we will store all this text inside a pandas data frame in order to manipulate it. And we're going to do all that in the upcoming programming lessons. I'll see you there. You know, I vividly remember learning about probability in school, and all my textbook exercises were constantly about urns. Always balls and urns, red balls from an urn, picking out a sequence of balls from an urn, picking out a particular ball out of an urn. Man, the memories.